All right, guys, so in this last video for Unit 3, we're going to be talking about an intro to the next type of function that we're going to be studying, which is the quadratic function. In fact, most of what we've done so far in this unit with complex numbers has been to get us ready to work with quadratic functions. So, a quadratic function is any equation of the form ax squared plus bx plus c. And we're going to put this restriction that the leading coefficient a cannot equal 0. If it does equal 0, then it really just becomes a linear function. So a parabola then is the graph of a quadratic function, and we'll take a look at a couple of those in just a little bit. We're going to start by just making sure that you can distinguish between a quadratic function and other types of functions, namely linear functions. So linear functions, let's go ahead and take a look at the table here. So if we take our x values and substitute them into our equation, I'm starting with 0. 2 multiplied by 0 is 0, plus 1 is 1. Then substituting 1, 2 multiplied by 1 is 2, plus 1 is 3. And then we'll continue to do that. Substitute 2 into your equation. 2 multiplied by 2 is 4, plus 1 is 5. And then you can probably see what the pattern is. We are really just going up by 2 each time. So the next one would be 7, and the next one would be 9. Let's do the same thing for our quadratic function. So our quadratic function is x squared plus 1. So starting with x is 0. If we put 0 in for x, 0 squared is 0, plus 1 is 1. So they both started kind of the same way. For the next one, 1. So we take 1 and squared is 1, plus 1 is 2. So it's going up a little bit more slowly, at least at first. Next is going to be 2. 2 squared is 4, plus 1 is 5. So at this point, we've kind of already caught up to where our linear function was. By the time we get to 3, 3 squared is 9, plus 1 is 10. We've already gone past where our linear function was. And by the time we get to 4, 4 squared is 16, plus 1 is 17. We have definitely surpassed where our linear function was at that point. So let's talk about the difference in the differences. In other words, what are you going up by each time? Well, for our linear function, we are going up by a constant 2 each time. So linear functions have a common, what's called first difference. Let's take a look at our quadratic. And so for the first one, we went up by 1, then we went up by 3, then by 5, then by 7. So we weren't going up by a constant ratio just yet. But let's take a look at those numbers we just found. From 1 to 3, we went up by 2. 3 to 5, up by 2. 5 to 7, up by 2. So rather than having a common first difference, quadratics have a common second difference. So as you're looking at either tables or points, that's what you're looking for to distinguish, do I have a linear function or do I have a quadratic? So let's do that with a few examples here. So starting off with in our tables. So in our table, for example, A, let's first see how much we're going up by. So up by 1, 3, 5, and then 7. So this one should be pretty easy since we just got done with a similar problem. And the second time up by 2. So this would be a quadratic. The explanation would be a common second difference. Let's take a look at B then. So an example B. And notice that our x variables are changing. They're going by 2. And so we shouldn't have to worry about it, but you always want to check and make sure that they're at least going up by a constant value. So let's see, from 8 to 2, down by 6, 2 to 0, by 2. And since those are negative, I better put a negative sign in front. And then 0 to 2, up by 2. 2 to 8, up by 6. So then from negative 6 to negative 2, I would have gone up by 4. Negative 2 to 2, also up by 4. 2 to 6, also up by 4. So actually this one also ends up being quadratic. And again, we've got a common second difference. Now we get to some equations. So for example, C. We've got that y is equal to negative 3x plus 20. Notice that that's only negative 3x to the first power. And what we said was that they had to be of the form ax squared plus bx plus c. And a couldn't equal 0, which means that you have to have this term with x squared somewhere in your equation. And we don't have that on c. So this is not quadratic. And the reason being, so our explanation, there is no x squared term. So then let's take a look at D. So we've got y plus 3x squared equals negative 4. Now, typically we want to have y by itself, so let me just move the 3x squared over real quick. You probably don't have to do this step. You could probably already see what type it's going to be. So we end up with y equals negative 3x squared minus 4. This time we can say that it is quadratic because the x squared term is there. All right. Finally, let's take a look at some points. Now, for points, just like in a table, you're going to focus on the y values. So the y values, you're going from 4 to 1, that's down by 3. 1 to 0, down by 1. 0 to 1, up by 1. 1 to 4, up by 3. And then from negative 3 to negative 1, you went up by 2. Negative 1 to 1, up by 2. 1 to 3, up by 2. So this is also going to be a quadratic. And again, that's because of the common second difference. All right, one last example before we take a look at graphs. So on this last one, you're going from 9 down to 2, so down by 7. 2 to negative 1, you went down by 3. Negative 1 to 0, you went up by 1. And 0 to 7, you went up by 7. So the negative 3 to negative 7, we went up by 4. Negative 3 to 1, we went up by 4. And then 1 to 7, though, we went up by 6. So notice that we're not going to be able to say that this is quadratic. And that's because it has no common second difference. Now, we don't know what it is. We just know that it's not quadratic. All right, so at this point, hopefully you would be able to tell by looking at either a table or an equation or a set of points whether a function was quadratic or not. So now let's go ahead and talk about how you'd be able to distinguish its graph. And we're going to do that by taking a look at a couple of those graphs. Let's start on example A by looking at the graph y equals x squared. And we're going to do that the long way by using an XY t-chart. So for the x values, we're just going to go from negative 2 to positive 2, putting those into our equation y equals x squared. So essentially, we're just taking each number and squaring it. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So then graphing each of those as a point, we'll start at negative 2 comma 4, negative 1, positive 1, 0, 0, positive 1, and positive 2, positive 4, to give us this kind of U-shaped graph, which we saw a little bit of in Unit 1, which is our quadratic function. Let's see how that changes for example B. So example B, we've got a similar equation, y equals this time negative x squared. So we're going to square the number and then put a negative in front of it. So negative 2 squared is 4, but then put a negative in front, it's negative 4. Do the same thing with negative 1. So negative 1 squared is 1, put a negative in front, is negative 1. For 0, it's really not going to matter. 0 squared is still 0, put a negative in front, and it's still 0. There is no negative 0. And then for 1 and 2, you also end up with negative 1 and negative 4. So let's go ahead and graph this function. So we've got negative 2, negative 4, negative 1, 0, 0, 1, negative 1, and 2, negative 4. So a similar shape to the graph, it's just opening in the other direction. So in other words, if you remember our transformations from Unit 1, that negative in front would be a reflection over the x-axis, which is in fact what happened when we looked at the graph. So let's talk about some of the characteristics that we'll notice. So the graph of a quadratic function, we already know that that is called a parabola. every parabola is going to be U-shaped. So it's going to look like the letter U. It's either going to open up or it's going to open down. All parabolas are going to be symmetric. That is, that every graph has an axis of symmetry. And that axis of symmetry is going to be a vertical line. What that means is that it's always going to be written as x equals and then a number. The vertex is going to be a special point. So the vertex is always going to be the highest or lowest point on the parabola. You might remember those if it opens up. So if our graph looks something like this, then that point at the bottom, remember, we called a minimum. Whereas if it opens down, then this point that's at the top, remember, we're going to call a maximum. They would also be referred to as a relative minimum and maximum, if you remember that vocab from Unit 1. The points where the graph crosses the x-axis are known as a few different things. Let me start with zeros. They're also known as roots. And then obviously where it crosses the x-axis is also known as x-intercept. So lots of different names that you can use for where the graph crosses your x-axis. And then the y-intercept is wherever the graph is the point on the graph where your x value is 0. So whenever you want to find the y-intercept, just put 0 in for x. Okay, so let's label this graph with a few of those vocab terms. Starting off with the vertex. Remember, the vertex is the highest or lowest point, the max or min. So that would mean that this arrow pointing towards that point would be our vertex. The axis of symmetry is the vertical line which goes through the center of our equation. So that would be this line right here, so axis of symmetry. You will sometimes see that abbreviated, so let me mention that as well. AOS for axis of symmetry. Finally, for zeros, remember that those are where the graph crosses your x-axis. So the two arrows pointing to those 2 points would be right here. So let's go ahead and find some of those points. So starting off with, what is the y-intercept of the parabola above? So where does it cross the y-axis? That happens at -3. So 0, -3 would be our y-intercept. How about the roots? The roots, remember, are the same as the zeros. There are 2 of those. One of them is at -1, 0. The other is at 3, 0. Now, is the vertex a maximum or a minimum? In this case, it is a minimum. Let's talk about a couple more things. So the axis of symmetry, let's go ahead and write the equation for that. So we're going to say x equals and then the number that it's going through. So in this case, that equation would be x equals 1. Next, let's go ahead and write what the vertex is. The vertex would be that point that it's looking at. So that would be the point 1, -4. All right, let's talk about 2 more things and then we'll call it a day. Let's talk about the domain and range for this graph. So the domain for this graph is going to be all real numbers. Notice that it is going to the left and to the right forever. The range is not going to be all real numbers. Notice that there is a lowest point. In fact, the lowest y value on the graph is at -4. And everything else above that works. So as long as y is greater than or equal to -4, that's going to be our range. All right, guys, that's all we've got for Unit 3. Until next time, have a great day.